Hi everyone, welcome to machine learning, and today we want to take you through bagging model, which stands for Bootstrap Aggregating. It works by splitting the dataset in different versions and run the model on these versions and aggregate the result to come up with the final prediction. So it works with any model. For example, in this case, we want to see how we can do bagging with random forest. We run random forest on several versions of our dataset and we come up with a final decision. So the first thing is to load our dataset, which is TOR, that's the name of the dataset, RDA, that's the file with the dataset. So the file is an RDA file which contains our dataset. So our dataset is already splitted in two different sets, which is the train and the test. So, but I'm going to show you how we do the splitting. So the first thing is to do set seed, then you specify the set seed you want so that you'll be able to reproduce the results. Then the next thing is to create a train index, right? So the train index, then you use the sample function to do random sampling. So I'll start from 1 to n rows of my data. N row just means the number of rows of my data. Then you specify the size. So this is the time where you specify if you want to do an 80%, 20% split or a 70%. It all depends. So we are going to use an 80% 20 split. Then you specify the number of rows of the data. I'm not going to run this because I have already done this. So the next thing is to create the train set. So the train set is going to be from the data. We take the indices, which we have created here. So I'm going to say train index. So on the number of rows, I'm only taking those which are in my train index, and they were randomly selected through the sample function, and I need all the columns, so I won't write anything after the comma. So the next thing is to do the test set, which is the opposite of what we have done. So I'm going to say on my data set, I need anything that is outside the train index, right? So I run this. So by doing this, we now have the train set and the test set, right? So back to my original data set, I have a train DB, which is part of my data set. So I'm going to take a summary so that you see what I mean. Train DB, that's my data set, which is in this file, the RDA file. All right, so this file is also in the description. You can download it, and just the summary shows you more about the variables in the data set and if there are missing values or there are no missing values. And also today we are focusing on our response variable, which is the label. It's in two different classes, which is non-TOR and the TOR. So we want to predict whether the internet, so the dataset is about internet connection, whether the internet connection is coming from the TOR or it's coming from the non-TOR. It helps us understand to identify the dark web. So that's it. That's what we have now. So the next thing is to run the model. So I'll go to the model. Like I said, we are using bagging on random forest. So right, we specify the library. Then I'm going to call it bag mod. You can name anything you want. This is just me naming the model. So I'm going to use random forest. Then I'm going to specify my response variable, which is label. Then I use tilde to specify that I'm going to work on all explanatory variables. I won't list them one by one. Then the next thing is to specify the data, which is going to come from the train set, which is train DB. Then the next thing is to specify the number of trees that I want to create. These are the separate samples, number of trees. So I wanted them to be 200 trees. And mtry now. So mtry normally works by specifying the number of variables which I want to be in these specific random datasets, specific versions of my dataset. So for random forest, you need to specify a number not all the variables. For bugging model in random forest, you specify all the columns, right? So that's how bugging and random forest are different. So I'm going to say number of columns of my train db, and I'm going to subtract 1 because I want to remove the response variable from the number of columns. I just want only the explanatory variables, right? So anything remains the same, like node size. I'm gonna use a node size of 1, which is a deep tree. The smaller this number, the deeper the tree, right? So after doing this, you can now run the model. Running the model, the next thing is to do prediction. So I'm going to call this big pred. So I'm creating a matrix for predictions. So pred, I specify my model, which is mod, and I specify the unseen data, which is the test ed, which is my test set. Then I specify the type. The type will be the probe. So there are two types. You can write probe or response. If you write probe, it means you are going to get probabilities of getting a specific test class. If you write response, you get the actual classes. That's the difference. So this is just a matrix. If you want to see it, this is just a matrix. So it's a matrix which shows different classes and their probabilities, right? So the next thing is to create a class. I'm going to create a class. I'm going to call it a class. This is just a vector which is going to hold my predictions, right? So I'm going to say replicate. So what I'm replicating is the non-TOR, which is the first class here. I'm going to say non-TOR, and I want it to be replicated how many times, and row number of times. As I want it to be as big as the prediction matrix, right? So I will just, for me to match it, I'll just put the number of rows of that prediction matrix, right? So I'm creating a vector which is non-TOR throughout. So that's the vector now, and how I want to improve this or to use this vector is I'm going to take from the prediction matrix, which is big with the predictions, and from this prediction I want it to focus on the, as you can see, I want us to focus on the second column because already we have the non-TOR. So now let's focus on the second column to work with the TOR. So I'm going to say true. So what I'm doing now is I'm saying all those probabilities that are greater than or equal to 0.5, I want them to be the TOR, which is the TOR, right? So I'm replacing on my bag class. You see that we once had all non-TOR, now we have TOR. These are the replacements where the probability is greater than or equal to 0.5, right? So this is our new vector with all the classes, right? So the next thing is to create a table which we have our predictions. So I'm going to say prediction is going to be big class. So these are the predictions which are the ones here, and the actual is going to be what we had before, which is the test bd db of the label, right? So this is our table. For us to better see it, we are going to create a confusion matrix, but for us to use a confusion matrix, we need a library called caret, which stands for classification regression trees. Then we call the confusion matrix and this is T. Specify the positive class. We want the positive class to be the TOR. That's our sensitivity class, right? So here we are, we have the confusion matrix, and now we can work on the confusion matrix first before the statistics. We can see that these are our predictions. We predicted a non-TOR or non-TOR of 11,888 correctly as it is in the dataset, which is actual. So we correctly predicted the non-TOR, which is true negative, and also we falsely predicted a TOR of 88 TOR, we predicted them as non-TOR, which is false positive. Then we correctly predicted the TOR of 1,520 as TOR, which is true positive, and we incorrectly predicted TOR as non-TOR of 68, which is false positive, right? So these are the predictions that in comparison. The next thing is to look at the accuracy. We can see we have a 98% accuracy, which is pretty well. It shows that the model was correct 98 times of the time, so that's good. The next thing is to see the confidence interval. Shows the accuracy is ranging from 98 to 99, which is good. Look at the no information rate. It shows 88%. What it means is if the model was to predict the most frequent class every time, it was going to have an 88% accuracy, which is less than the 98% accuracy of the whole model. Then if that happens, it means the model is good. In the comparison of the accuracy and the no information rate is less than the p-value is less than 0.05, which shows that's a very significant comparison. And our kappa, which shows the agreement between the predicted value and the actual value, which is 94%, a 1%, 100%, or a 1. It means there's a perfect agreement. A 0 means there's a poor agreement. So a 0.94 value means it's an excellent kappa agreement. And we look at the sensitivity. We are seeing that we're able to predict 94% of the positive class, which is the TOR, and sensitivity we're able to predict 99% of the TOR, non-TOR, which is the negative class. So what it shows is there could be the reason why we have a high negative prediction is probably because the data is imbalanced. We have more negative, which is non-TOR, than the positive. So it's all about the data set. However, we have good accuracy and good sensitivity and specificity. So our model is good. That's fine. The next thing is to check now the feature selection, which features are we performing well, and which features are important to our model. So we're going to use a var import plot. Then we specify the model, right? So there are a number of variables here, so we limit them, and is equal to 10. Right, so it shows these are the very important variables to our model. How this method works is it uses a mean decrease gene. So we want to see if we don't have a certain variable, what will happen to our impurity. Is it going to decrease? How is it going to decrease? So that's how they are going to be ranked. So if we don't have this BWD variable, we are going to lose our impurity by this probably 4,000 mean decrease gene. So it means this variable is very important. That's how, and it happens also to the next variables. So yeah, that's it. That's a very powerful model, baking random forest. It's a very powerful model. And also, however, we used mean decrease gene, but it also have its weaknesses, and new technology is working towards getting another good matrix that can help to come up with good variable importance. So, but that's a video on its own. So thank you so much for watching this video and understanding how the baking model works. Right, see you in the next video.